بسم الله الرحمن الرحيم، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه وسلم أجمعين. مع حضراتكم الدكتور محمد عباس، أستاذ الصيدلانيات ومشارك في جامعة الملك سعود. كل عام وحضراتكم جميعا بخير وصحة وسلامة. نسأل الله سبحانه وتعالى أن يرفع عن أمتنا البلاء وأن يحفظ أهلنا جميعا أينما كانوا. إن شاء الله تعالى اليوم أنا أرحب بحضراتكم في مناقشة رسالة الصيدلي عبدالله الشهري المقدمة في قسم الصيدلانيات بجامعة الملك سعود. عنوان الرسالة Application of Quality by Design Approach in the Optimization of Apigenin Nanonization by Planetary Mill. إن شاء الله نشرف اليوم بوجود يعني لجنة التحكيم على الرسالة، سعادة الأستاذ الدكتور جمال محمد محروس وسعادة الأستاذ الدكتور فارس العنزي، أساتذة أو أستاذي الصيدلانيات بكلية الصيدلة جامعة الملك سعود. إن شاء الله عبد الله اليوم سوف يقدم عرض موجز عما تم في الرسالة في غضون 30 دقيقة، يتبعه إن شاء الله تعالى فتح المجال للحضور إذا كان هناك بعض الأسئلة أو الاستفسارات. تفضل يا عبد الله.
بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. رئيس لجنة المناقشة ومشرف الرسالة الدكتور محمد عباس، أعضاء لجنة المناقشة الكرام الدكتور فارس العنزي، الدكتور جمال محروس، مشرف الرسالة المساعد الدكتور سلطان الشهري، المتابعين الكرام من أعضاء هيئة التدريس وطلاب ومهتمين، السلام عليكم ورحمة الله وبركاته. أرحب بكم وشهر مبارك عليكم وكل عام وأنتم بخير، وأسأل الله أن يرفع عن بلادنا وبلاد المسلمين أجمعين هذا الوباء وأن يديم علينا الأمن والأمان. My thesis title is Application of Quality by Design Approach in the Optimization of Apigenin Nanonization by Planetary. My presentation will be divided into 3 parts: introduction, optimization of Apigenin nanoparticle, characterization of optimized Apigenin nanoparticle formula. In introduction, I will talk about quality by design, nanotechnology, model drug in our study, Apigenin, and objectives of study. What is quality by design? Quality by design is a concept introduced by Dr. John in 1992. It is a systemic approach to pharmaceutical development with 3 defined objectives. It is described that the quality should be designed into a product by understanding the effect of both input materials and process and control them. Importance of quality by design. Most quality crises and problems relate to the way in which the product was designed in the first place. Application of quality by design approach can increase product quality, increase safety and efficiency, which improve the patient compliance. Economic benefits by reduce number of failed batches, save time and energy, increase process capability. Elements of quality by design are quality target product profile, clinical quality attributes, critical material attributes, critical process parameters, quality risk assessment, and design steps. Quality target product profile is a summary of quality characteristics of a drug product that ideally will be achieved to ensure the desired quality, like clinical use, dosage form, route of administration. Critical quality attribute is the physical, chemical, biological, or microbiological properties or characteristics of finished product that should be within appropriate limit, range, or distribution to ensure the desired product quality, like dissolution, particle size, and degradation. Critical material attribute is a physical or chemical or biological or microbiological property or characteristics of starting material, such as EBI, excipient, that should be within appropriate limits, range, or distribution to ensure the desired quality. Critical process parameters are process parameters that critically affecting the quality of drug final product. Example: speed, flow rate, temperature, or pressure. Quality risk assessment is a science-based process that identify critical material attributes or critical process parameter and critical quality attribute. There is several tools for quality risk assessment, like Ishikawa primary hazard analysis. Drug nanonization can improve drug solubility, permeability, and bioavailability. Can also improve targeting the drug to specific organ and control drug release. 95% of all new potential therapeutics have poor pharmacokinetic and biopharmaceutical properties. Therefore, there is a need to develop suitable drug delivery systems that distribute the therapeutically active drug molecules only to the site of action, without affecting healthy organs and tissue. Nanonization of API can result in enhanced solubility, permeability, and bioavailability by reducing particle size and increase surface area. Two major nanonization technologies are used. Top-down strategy, in which particle size is reduced from coarse to nanoscale. Top-down technology example are wet milling and high-pressure homogenization technique. Bottom-up strategy, which means generation of nanoparticle from drug molecules in solution by forming and controlling precipitation and crystallization. Bottom-up strategy include anti-solvent precipitation, different kind of liquid atomization. Planetary ball mill machine is milling machine depends on centrifugal acceleration force rather than gravitational acceleration force. Different kinds of balls can be used, like zirconium oxide and stainless steel balls. Apigenin is a natural flavonoid, a yellow crystalline powder, particularly insoluble in water. Apigenin has strong antioxidant and anti-inflammatory and anti-mutagenic, antiviral, and anti-cancer activities. Apigenin is a class 2 drug according to biopharmaceutical classification system, which has low solubility and high permeability characterization. Poor solubility of apigenin leads to low oral bioavailability. Objectives: based on previous introduction, the objectives of my study could be summarized as optimization of apigenin nanonization using pitch planetary ball mill by applying quality by design approach. Physicochemical evaluation of optimized apigenin nanoparticle formula. Stability study of optimized apigenin nanoparticle formula. And final with in vivo evaluation of optimized Apigenin nanoparticle formula. Rich planetary ball mill was used to manufacture Apigenin nanoparticle. As you see in the picture, zirconium ball, zirconium oxide balls were used as milling balls. First, we screened of some critical material attributes and critical process parameters. And second, selected three independent factors. To be included in the design of experiment. Thereafter, the impact of selected independent factors can critical factor on critical quality attributes as determined using statistical analysis. Finally, the risk severity of this factor was determined by risk assessment tools. Three stabilizers of 5% concentration were studied for their effect on Apigenin prepared by planetary ball milling. From the result, it's clear that the milling of Apigenin with 5% ppb resulted in lowest nanoparticle size and highest dissolution rate. Therefore, 5% ppb was used as nanoparticle stabilizer. Based on screening and previous studies, the design space was built as the follows. 5% ppb was selected as stabilizing agent for Apigenin nanoparticle. Zirconium ball with a size of 0.1, 0.5, and 1 millimeter, drag to solvent ratio of 0.04, 0.12, 0.2 were used. Different milling speed 200, 600, and 1000 RPM. The number of cycles was 3 cycles. Time of milling was 10 minutes for each cycle, and views time 5 minutes. Design of experiments to design the different formulation using software program. Design of experiments was applied to study the impact of selected independent factor, critical material attribute, and critical process parameter, high risk potentials on critical quality attributes of Apigenin nanoparticle. 3 levels. 3 power to power 3 full factorial design was used. The independent factors are the milling speed, milling pool size, drag to solvent ratio. Based on 3 to power 3 full factorial design, 27 nanoparticle formulations were prepared by different milling speed and different milling pool size and solid solvent ratio. The prepared Apigenin nanosuspension were freeze-dried, and the obtained nanoparticle were stored in tightly closed container protected from the light pending further studies. The prepared Apigenin nanoparticle formulations were characterized for their particle size, beta potential, nanoparticle content, and in vitro dissolution, initial dissolution rate, and dissolution efficiency. Result and discussion. The following figure shows the calibration curve of Apigenin in phosphate buffer pH 6.8 at 336 nanometer obtained spectrophotometrically. Effect of independent parameters on particle size. The analysis of variance for particle size of Apigenin nanoparticle formulation show that all size showed significant antagonistic effect on particle size of Apigenin nanoparticle. milling speed and solid solvent ratio had insignificant effect on particle size of Apigenin. However, quadratic effect of milling speed showed highly significant antagonistic effect on nanoparticle size. Main plot for the effect of independent parameter on Apigenin nanoparticle size showed that increasing milling ball size resulted in reducing Apigenin nanoparticle at low value. Response surface plot for the effect of milling ball size and speed in Apigenin nanoparticle size at constant solid solvent ratio 0.12 revealed that milling speed and ball size have the most effect on Apigenin nanoparticle size. Increasing milling speed resulted in reducing nanoparticle size at speed value up to 600 RPM. Thereafter, the effect is slight. In addition, increasing in milling ball size resulted in reducing nanoparticle size at all. This histogram shows particle size of different Apigenin nanoparticle formulation. The largest particle size was observed in case of nanoparticle formula number 8, in which the smallest ball size 0.1 millimeter was used with medium solid solvent ratio 0.12 and the lowest milling speed of 200 RPM. The lowest particle size was observed in case of nanoparticle formula number 15, in which the medium ball size 0.5 millimeter and solid solvent ratio 0.2 and milling speed of 600 RPM. Effect of independent parameters on zeta potential. Analysis of variance for the effect of independent parameters on zeta potential values of Apigenin nanoparticle formulation showed that the quadratic effect of milling speed on zeta potential has significant effect. Other parameters as milling ball size and direct solvent ratio had insignificant effect on drug zeta potential of Apigenin. The main individual plot and estimated response surface for the effect of independent variables on Apigenin nanoparticle zeta potential indicate that milling speed showed agonistic effect on drug nanoparticle zeta potential values from lower to medium speed level. This effect was revealed to be antagonistic at higher milling speed. Insignificant effect was observed in case of milling speed, milling ball size, and solid solvent ratio. The following figure shows the zeta potential value of different Apigenin nanoparticle formulation. The obtained data showed that highest zeta potential value was recorded in case of nanoparticle formula 8, in which the speed of 200 RPM, milling ball size was 0.1 millimeter, and solid solvent ratio was 2:1:2 ratio. In contrast, lowest zeta potential value was observed in case of nanoparticle formula 12, in which the milling condition was 1000 RPM and milling ball size was 1 millimeter and solid solvent ratio was 0.2. Effect of independent parameters on initial dissolution rate of Apigenin from different nanoparticle formulations. The analysis of variance indicate that solid solvent ratio showed very highly significant antagonistic on the IDR of Apigenin from nanoparticle formulation. Similarly, antagonistic effect, significant quadratic effect of milling speed was observed on the drug IDR. The main effect estimated the effect of independent factors on IDR of Apigenin from nanoparticle formulation showed that increasing solid solvent ratio resulted in a clear reducing of the IDR from nanoparticle. This might be due to increasing solid slurry facing the milling folds, which decrease the milling traction force. The histogram, this histogram shows that the initial dissolution rate of Apigenin from different nanoparticle formulations. The highest IDR was 43 after 5 minutes of Apigenin from nanoparticle formulation was noted in case of nanoparticle formula number 25, which was prepared by using milling speed of 600 RPM and smallest hole size 0.1 and low solid solvent ratio 0.04. The slowest IDR values of Apigenin from nanoparticle formulation were recorded with nanoparticle formulation number 9, prepared by using milling speed of R1000 RPM, milling hole size 0.1 millimeter, and highest solid solvent ratio 0.2. Final, the effect of independent parameter of Apigenin dissolution efficiency. The analysis of variance for the effect of independent parameter on dissolution efficiency of Apigenin from nanoparticle formulation indicate that solid solvent ratio have a highly significant antagonistic effect on dissolution efficiency of Apigenin. Also, the quadratic effect of milling speed showed significant antagonistic effect on dissolution efficiency. These results are typically correlated with the result of the effect of independent parameter on the initial dissolution rate of the drug from nanoparticle formulation. From the main effect plot and response service plot estimate that solid solvent ratio showed significant antagonistic effect on dissolution efficiency of Apigenin from nanoparticle formulation. As increased solid solvent ratio resulted in noticeable reduction of dissolution efficiency of Apigenin from the nanoparticle formulation. Milling speed showed an insignificant effect, but increasing milling speed reduction of dissolution efficiency of Apigenin from nanoparticle formulation was noted at low speed level. Among this, the all tested 27 formulation, Apigenin dissolution rate was found the highest from formula number 25, which was 64%. This nanoparticle formula was prepared by using 600 RPM and as milling speed, milling hole size of 0.1 millimeter, and very low solid solvent ratio 0.04. This is dissolution profiles of Apigenin from different nanoparticle formulations at 0.04 drug to solvent ratio. And this is dissolution profiles of Apigenin from different nanoparticle formulations at 0.12 drug to solvent ratio. Also, this is dissolution profiles of Apigenin from different nanoparticle formulation at 0.02 drug to solvent ratio. Risk assessment of potential factors affecting critical quality attributes of Apigenin nanoparticle prepared by planetary ball milling by primary hazard analysis tools. Red color indicate high risk, and yellow color indicate medium risk, and green color indicate lower risk. Upon studying the effect of independent process and formulation factors on Apigenin nanoparticle attributes, the risk assessment analytical tools showed that speed and milling ball size exerted high risk on nanoparticle size, while solid solvent ratio showed medium effect on the studied response. Solid solvent ratio and milling ball size exhibited high risk on nanoparticle zeta potential, while milling speed showed low risk. Moreover, solid solvent ratio exhibited high risk on both IDR and dissolution efficiency. While milling speed and milling ball size showed medium risk in these responses. Ishikawa fishbone diagram for the effect of critical material attributes and critical process parameter on critical quality attribute of Apigenin nanoparticle prepared by planetary ball milling. The following desirability items selected for optimized Apigenin nanoparticle formula were minimized particle size, maximized zeta potential, maximized initial dissolution rate, and dissolution efficiency. Based on previous desirability of optimized formula derived from statistical program, the following factors were obtained by software for preparation of optimal formulation: milling speed 666 RPM, milling ball size 0.1 millimeter, and drug to solvent ratio 0.04, which means 1 gram of Apigenin in 25 milli of water containing 5% ppb as milling solvent. The observed values were found close to predicted optimized values. From the nanoparticle formulation, observed particle size was 252 nanometer, and zeta potential observed value was -13 compared to predicted value -16. Also, IDR observed value was 59, and dissolution efficiency was 92%. Characterization of optimized Apigenin nanoparticle formula, physicochemical properties, and pharmacokinetic and stability studies. The optimized Apigenin nanoparticle formula was characterized by X-ray diffraction analysis, FDR, and DSC. Pharmacokinetic studies for optimized Apigenin nanoparticle formulation was carried out using male Western albino rats. 10 animals were allocated in two groups. Group 1 received untreated Apigenin orally. Group 2 received optimized nanoparticle formula orally. Before administration of the rats, pure Apigenin and our optimization formula of Apigenin were displayed in 5% sodium carboxymethyl cellulose aqueous solution in order to form suspension. Animals were provided for the free access to food and water 3 hours after oral administration of each sample. The drug was administered orally 10 milligram per kg by oral gavage in order to assure the dosage, the dose uniformity. 0.5 milli of blood sample was taken following time interval of 1, 2, 4, 6, 11, and 24 hours. Finally, plasma was separated through centrifugation of sample at 15,000 RPM and for 10 minutes, then kept at -18 till analyzed. Stability study were carried out for optimized Apigenin nanoparticle formula according to ICH guideline that was subjected to acceleration stability. Result and discussion. X-ray powder diffraction spectra of Apigenin, Apigenin and BPB physical mixture and optimized Apigenin nanoparticle formulation. Optimized nanoparticle formula. A partial reduction in the intensity of drug crystalline peaks was observed. FTR. In case of Apigenin nanoparticle formula, the stretching vibration band of Apigenin could be seen in the original. However, OH stretching band of BPB at 3,448 cm-1, and the drug carbonyl stretching band at 1,654 cm-1. This appeared indicate an interaction between the drug and the nanoparticle stabilizing volume. Drug concentration time profile test of Apigenin after administration of optimized nanoparticle formulation in comparison to the pure drug. It is clear that Apigenin nanoparticle formula showed plasma concentration significantly higher than untreated drug. Cmax of orally administered nanoparticle formula was 4-fold higher than that observed in case of untreated drug. Also, Tmax was 1.1 hour nanoparticle formula compared to untreated drug 6 hours. Indicates rapid absorption. This pharmacokinetics parameters for Apigenin optimized nanoparticle formula compared to untreated powder after oral administration in Western albino rats. Area under the curve for nanoparticle, Apigenin nanoparticle was about 2-fold higher than that noted in case of untreated drug, as shown in the table. Effect of storage on stability of optimized Apigenin nanoparticle formula for the optimized Apigenin nanoparticle formula. The particle size for initially prepared nanoparticle was 252 nanometers, which with zeta potential of -13.5. After 6 months of acceleration stability, the particle size increased to 381 nanometers. But no further increase in particle size was noted after 6 months. The solution profile of this of Apigenin profiles of Apigenin dissolution from optimized nanoparticle formulation at 3 and 6 months compared to the dissolution of fresh Apigenin nanoparticles and untreated powder showed a decrease in the dissolution of drug from nanoparticle formulation after 3 and 6 months, but is still significantly higher than that of untreated drug. The slight slowing of drug dissolution rate from nanoparticle formulation after 3 and 6 months stability may be due to increased particle size during storage. Conclusion: nanonization enhanced the dissolution rates and bioavailability of Apigenin. Many factors can be controlled to achieve optimization results, including formulation and process parameters. Apigenin in vitro dissolution from nanoparticle formulation was enhanced in comparison to untreated drug, and this could be attributed to the reduction in particle size and the use of the BPP as stabilizer. The application of quality by design approach in the formulation of Apigenin nanoparticle prepared by Planetary ball milling can help formulator in detailed understanding of the effect, critical material attribute, and critical process parameter on the critical quality of the final product. Apigenin nanoparticle formula showed plasma concentration significantly higher than untreated drug. Cmax of oral administrative nanoparticle formula was about 4-fold higher than that observed in the case of untreated drug. قبل نهاية العرض أشكر الله سبحانه وتعالى على توفيقه وفضله، له الحمد والشكر من قبل ومن بعد. أشكر مشرفين الكرام الدكتور محمد عباس والدكتور سلطان الشهري على كل ما قدموه لي من دعم ومساعدة وتدريب وتعليم. أشكرهم كل الشكر، لهم حقيقة فضل كبير علي، وأسأل الله أن يجزيهم خير الجزاء. أشكر أيضا لجنة المناقشة البروفيسور فارس العنزي والبروفيسور جمال محروس. كل الشكر لكل الكيالي على ما قدموه من دعم، على رأسهم البروفيسور فارس العنزي وجميع الدكاترة الكرام. كل الشكر للدكتور إيهاب الزيات على دعمه. كل الشكر للدكتورة دعاء على دعمها ومساعدتها لي في هذه المرحلة، وكذلك للبروفيسور فهد الجنوبي على دعمه أيضا. أشكر زملائي الكرام سعيد القحطاني والزميل أسيد والزميل بندر على دعمهم. كل الشكر أيضا لجميع أعضاء هيئة التدريس في قسم الصيدلانيات في خاصة وفي كلية الصيدلة عامة. الشكر موصول لوالدتي العزيزة ووالدي العزيز، فلولا الله ثم فضله ما وصلت لهذه المرحلة. الشكر موصول لزوجتي وأخواني وأصدقائي جميعا، وأخيرا لهيئة الغذاء والدواء حيث أتاحوا لي الفرصة لإكمال دراستي. أشكر زملائي الكرام في إدارة تسجيل المنتجات البشرية، وكذلك مديري المباشر حمود الحربي على دعمه وتعاونه الكبير معي. الصلاة والسلام على أشرف الأنبياء والمرسلين. وأي أسئلة تفضل.
شكرا لك يا عبد الله على هذه المقدمة.